June 7, 1944. Gold Beach, Normandy, France. Major General Percy Hobart stood knee-deep in seawater as concrete blocks the size of 3-story buildings floated past him toward their designated positions offshore. Around him, Royal Engineers shouted coordinates while American construction battalions maneuvered Phoenix caissons weighing over 6,000 tons through channels barely cleared of mines hours earlier. German artillery shells whistled overhead, landing with geysers of spray among the assembling harbour components. This was not supposed to be possible. Every military engineer in Europe, British and German alike, understood the fundamental axiom of amphibious warfare. Invasions required ports, armies needed existing harbours with their cranes and warehouses, their breakwaters and docking facilities, their shelter from storms and protection from enemy action. Yet here, less than 24 hours after the largest amphibious assault in human history, Allied forces were assembling artificial harbours from components manufactured in England, towed across the English Channel, and positioned under fire to create port facilities where none had existed the day before. The German High Command had built their entire defensive strategy on the impossibility of what Hobart was watching unfold. Oberkommando der Wehrmacht planners had calculated that any Allied invasion would collapse within weeks without captured port facilities. They had fortified every significant harbour from Norway to Spain with millions of tons of concrete and steel, confident that defence of these fixed positions would defeat any landing. Field Marshal Rommel had personally inspected these fortifications and declared them impregnable. German military doctrine, tested across 2 world wars, held that invading forces needed harbours within days or face destruction through supply collapse. The concrete floating past Major General Hobart represented the destruction of that doctrine. The massive Phoenix caissons, the floating bombardment breakwaters, the articulated steel roadways called whales, the countless caissons and pierheads and anchoring systems, all of it defied what German planners believed physically possible. Yet it was happening. The mathematics of impossibility were being rewritten in reinforced concrete and welded steel, in hydraulic systems and tidal calculations, in the revolutionary concept that German assumptions about Allied capabilities were catastrophically wrong. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The seeds of this impossible achievement had been planted years earlier, in meetings where British engineers faced a strategic problem with no apparent solution. The disaster at Dieppe on August 19, 1942, had demonstrated with brutal clarity that direct assault on fortified ports meant suicide. Over 6,000 Allied troops, predominantly Canadian, had attacked the French port city in Operation Jubilee. German machine guns positioned in concrete casemates atop white chalk cliffs had cut down wave after wave of attacking soldiers. 27 Churchill tanks had rumbled onto the shingle beach. Every single one was destroyed or abandoned. The casualty figures staggered military planners. Of the 4,963 Canadians who embarked that morning, only 2,210 returned to England, many of them wounded. Canadian casualties alone numbered 3,367, including 916 dead and 1,946 prisoners of war. The Royal Navy lost 75 killed and 269 missing or captured. The Royal Air Force suffered 62 fatalities in the skies above Dieppe. German casualties barely exceeded 600. The raid lasted less than 9 hours from first landing to final evacuation. Those 9 hours had taught the Allies the most expensive lesson of the war. Any future invasion of Fortress Europe would require capture of a major port to sustain the assault. Yet Dieppe proved beyond doubt that German defences made direct assault on fortified harbours suicidal. Major General John Hamilton Roberts, commanding the 2nd Canadian Division, wrote in his after-action report, later discovered in the National Archives of Canada, the strength of German port defences exceeded all intelligence estimates. Concrete casemates housing heavy artillery proved impervious to naval bombardment. Machine gun positions enjoyed interlocking fields of fire across every approach. The port facilities themselves were prepared for demolition at the first sign of attack. Even had we captured Dieppe intact, German counterattacks would have reclaimed it within 48 hours. The strategic paradox became inescapable. The Allies needed ports to invade Europe, but the Germans had fortified every port from Norway to the Spanish border. By December 1943, Field Marshal Rommel had completed his inspection tour of Atlantic defences. His confidential assessment, preserved in German military archives at Freiburg, revealed his concerns about the overall defence concept. His solution was characteristically aggressive. Rommel ordered the implementation of millions of mines along potential invasion beaches. He demanded concrete pillboxes at every strategic point. He personally supervised the installation of beach obstacles designed to rip the hulls from landing craft. Rommel's asparagus, tall wooden poles with sharpened tops and explosive charges, sprouted across fields behind the beaches to impale gliders and paratroopers. More critically for Allied planning, Rommel fortified the ports with fanatical thoroughness. In a memorandum to Hitler dated December 31, 1943, Rommel wrote, "The enemy's main concern will be to get the quickest possible possession of a port or ports capable of handling large ships." Hitler designated 11 major ports as Festungen, fortresses to be defended to the last man: Dunkirk, Boulogne, Le Havre, Cherbourg, Saint-Malo, Brest, Lorient, Saint-Nazaire, the Gironde River estuary leading to Bordeaux, and the Channel Islands received priority for men and materials. Each fortress boasted heavy naval guns in reinforced concrete emplacements, artillery batteries covering every approach, anti-aircraft positions, minefields extending miles into the surrounding countryside, and garrisons prepared to fight to the death. The German defensive philosophy rested on an assumption so fundamental that no senior commander questioned it. An invasion force required capture of a major port within days of landing or face defeat through lack of supplies. This assumption had governed military planning since ancient times. Armies needed harbours for their supply ships, dockyards for repairs, cranes for unloading heavy equipment, warehouses for stores, and protection from storms that could scatter and destroy an invasion fleet. General Dwight D. Eisenhower, appointed Supreme Commander of the Allied Expeditionary Force in January 1944, understood the problem with crystal clarity. In his personal diary entry from March 1943, preserved at the Eisenhower Presidential Library, he noted, "We face an impossible choice: attack a heavily fortified port and suffer catastrophic casualties in the assault, or land on open beaches, and watch our supply lines collapse within weeks. Either course leads to defeat. The alternative that emerges from failure at Dieppe may represent our only hope, though it defies all conventional military wisdom." What Eisenhower called the alternative had begun germinating in the minds of British engineers even before the Dieppe disaster. The concept traced its roots to 1917, when Winston Churchill, then First Lord of the Admiralty, had proposed using flat-bottomed barges and manufactured caissons to create an artificial harbour for planned operations against Dutch coastal islands during the Great War. The war ended before the scheme could be tested, but Churchill never forgot the idea. In the spring of 1942, weeks before Dieppe, Churchill attended a conference where the impossibility of capturing a port came up for discussion. His response, recalled years later by multiple attendees, including Admiral Louis Mountbatten, electrified the room. "Piers for use on beaches. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves." That directive, issued on May 30, 1942, consisted of fewer than 100 words. It changed military history. The engineering challenges seemed insurmountable. How do you build a harbour capable of handling hundreds of cargo vessels? How do you transport thousands of tons of concrete and steel across open water? How do you assemble such a structure under enemy fire? How do you anchor it to the seabed in tidal waters that rise and fall 20 feet twice daily? How do you protect it from the violent storms that plague the English Channel? Each question spawned a dozen technical problems that would require solutions never before attempted in maritime engineering. Mountbatten assembled a team at the War Office that included Britain's finest civil engineers, naval architects, and construction specialists. Their initial meetings at the Institution of Civil Engineers on Great George Street in Westminster produced more questions than answers. The sheer scale of what Churchill demanded seemed to violate the laws of physics and common sense. Lieutenant General Frederick Morgan, Chief of Staff to the Supreme Allied Commander, and his Cossack planning team calculated the requirements. The artificial harbours would need capacity equivalent to the port of Dover, Britain's busiest cross-channel harbour. Dover handled approximately 12,000 tons of cargo daily in peacetime operations. The invasion force would require facilities capable of landing 10,000 tons of supplies and equipment daily at each of the two planned harbour sites. That meant creating from scratch port facilities matching Britain's most developed harbours, then transporting these facilities across the English Channel, then assembling them on exposed beaches, then making them function while under potential enemy attack, all within weeks of D-Day. The timeline alone appeared impossible. Traditional harbour construction required years of work. The massive breakwaters protecting established ports had taken decades to build. The concrete and stone structures forming harbour walls represented investments of millions of pounds and countless man-hours. Yet Morgan's planning team concluded that the artificial harbours needed to be operational within days of the invasion, not months or years. Without functioning port facilities landing supplies by D-Day +2, the invasion would bog down and potentially collapse before Cherbourg or any other established port could be captured and repaired. The Germans, anticipating that any invasion would target existing ports, had prepared comprehensive demolition plans for every harbour facility along the coast. Even after capture, British engineers estimated it would require weeks to clear the wreckage and restore basic functionality to any port the Germans had defended. The concept that emerged from these planning sessions represented a fundamental reimagining of what harbours could be. Instead of permanent structures built over decades, the artificial harbours would be temporary facilities constructed in pieces, assembled rapidly, and designed to function just long enough to establish a secure lodgment in France. Instead of relying on natural geography for shelter from storms, the harbours would create artificial protection through floating breakwaters and sunken ships. Instead of fixed piers, the harbours would use floating roadways that could accommodate the extreme tidal variations of the Normandy coast. The planning team designated the project Mulberry, after the mulberry tree, for no reason more profound than it appeared next on the Admiralty's alphabetical list of code names for operations. 2 complete harbour systems would be built. Mulberry A would serve the American sector at Omaha Beach. Mulberry B would serve the British and Canadian sector near Arromanches. Each harbour required components that pushed the boundaries of engineering possibility. The Phoenix caissons formed the foundation of the Mulberry concept. These were massive reinforced concrete boxes, hollow inside, designed to be floated across the channel and then sunk into precise positions to form breakwaters and pier foundations. The caissons came in multiple sizes, but the largest measured 200 feet long, 60 feet wide, and 60 feet tall. When flooded with water, these structures weighed over 6,000 tons. The concrete walls measured 5 feet thick at the base, reinforced with steel bars in complex patterns designed by structural engineers who had never tackled problems of this scale in maritime environments. Each Phoenix caisson represented a construction challenge equivalent to building a medium-sized apartment block, except this apartment block had to float, be towed across open water, sink in a controlled manner, and then provide a stable foundation in tidal waters that would pound it with storms for months. Building them required solving problems that conventional harbour engineering had never faced. The caissons had to be light enough to float while empty, yet strong enough to withstand being towed in rough seas, then stable enough when flooded to resist the immense pressures of waves and tides. The concrete mix had to cure to full strength despite the aggressive saltwater environment. The internal compartments needed valves and flooding systems that would sink the caisson evenly rather than capsizing it. The external walls required fittings for anchors, mooring lines, and the connections that would link multiple caissons into a continuous breakwater. The construction program required building over 200 Phoenix caissons in less than 1 year, while Britain fought a total war on multiple fronts. Every resource was scarce: cement, Steel, timber, labour, transport, everything was needed for a dozen other urgent priorities. Yet the Mulberry project received what it needed because Churchill and Eisenhower understood its strategic necessity. Construction sites sprang up along river estuaries and coastal locations across southern England. The Thames Estuary, the Medway, the Southampton Water, the River Yeo near Appledore in Devon, all became massive construction yards where caissons took shape. The process began with excavating dry docks or creating temporary cofferdams. Workers poured concrete foundations, then erected wooden formwork defining the caisson's shape. Steel reinforcing bars were positioned according to engineering specifications that required precision normally associated with structural buildings, not maritime construction. Then concrete was poured, mixed to specifications developed specifically for the Mulberry project. The mix included special additives to accelerate curing and enhance resistance to saltwater degradation. Each caisson required thousands of cubic yards of concrete and hundreds of tons of steel reinforcement. As the concrete cured, workers installed the internal systems, valves that would control flooding, pumps for dewatering if needed, mounting points for anchors and mooring equipment, access hatches and ladders for maintenance crews, navigation lights. The attention to detail rivaled that of shipbuilding, applied to structures more massive than any ship. Once construction was complete, the dry docks were flooded and the caissons floated out. Tugboats towed them to assembly points where they awaited the invasion date. This process repeated at dozens of locations simultaneously throughout 1943 and early 1944. The industrial coordination required rivaled that of building the invasion fleet itself. The Bombardon floating breakwaters represented a different engineering approach to the same problem of creating shelter from storms. These were massive steel structures shaped like crosses, approximately 200 feet long and 25 feet in diameter. They floated on the surface, anchored to the seabed, and were designed to dissipate wave energy through their unique cross-shaped design. When waves hit the bombardons, the structure's shape caused the energy to be dispersed rather than transmitted. The theory was elegant, but implementation required solving problems of metallurgy, buoyancy, anchoring, and assembly that pushed British engineering to its limits. Each bombardon weighed approximately 1,600 tons and required specialized construction facilities. The steel fabrication demanded precision welding on a scale rarely attempted in maritime applications. The ballast systems that kept the bombardons floating at the correct depth required careful calculation and testing. The anchoring systems needed to hold these massive structures in position despite tides, currents, and storm forces. 24 bombardons were planned for each Mulberry harbour, forming an outer breakwater that would calm the seas before waves reached the Phoenix caisson lines. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The pier systems brought yet another set of engineering challenges. Traditional piers were fixed structures built on pilings driven deep into the seabed. The Normandy coast, with its extreme tidal, variations of up to 20 feet between high and low tide, made fixed piers impractical for rapid construction. The solution was the WWII, a flexible floating roadway system that could accommodate tidal changes while supporting fully loaded trucks. The WWII consisted of floating steel pontoons, each 80 feet long and 25 feet wide, linked by flexible joints that allowed the roadway to undulate with the waves while maintaining a relatively stable surface. The pontoons were connected to shore and to offshore pierheads by articulated steel spans. These spans could flex to accommodate the rising and falling tide while supporting vehicles weighing up to 40 tons. The engineering required to create a roadway that was simultaneously flexible and strong enough to carry heavy military vehicles represented innovation at the bleeding edge of structural design. Lieutenant Commander Alan Beckett of the Royal Engineers led the WWII development team. His initial designs drew skepticism from traditional harbour engineers who doubted that articulated roadways could withstand the stresses of sustained use in maritime environments. Beckett's breakthrough came from studying snake locomotion, recognizing that flexibility at joints combined with rigidity within spans could create a structure that adapted to environmental changes while maintaining functionality. The whale pontoons were manufactured across Britain in facilities that normally produced very different products. Shipyards, steel fabrication plants, and engineering works all contributed components. Each pontoon required precise construction tolerances. The steel hulls had to be watertight, the ballast systems had to maintain proper floating depth, the joint connections had to allow flexibility while transmitting structural loads. Quality control was critical because failure of a single pontoon in the chain could render an entire pier unusable. The pier heads that the whales connected to represented another engineering marvel. These were massive steel structures, 240 feet long and 60 feet wide, supported by floating steel boxes called spud pier heads. These structures had retractable legs, spuds, that could be lowered to the seabed to stabilize the pier head while still allowing it to rise and fall with the tide. The spuds were hollow steel columns, 5 feet in diameter, that penetrated through the pier head structure. Hydraulic systems raised and lowered them. When lowered, the spuds dug into the seabed under the pier head's weight, creating a semi-stable platform. When raised, the entire pier head could be towed to a new location. 7 of these spud pier heads were planned for each Mulberry harbour, providing multiple loading points where Liberty ships and other cargo vessels could tie up and unload directly onto trucks that would drive across the whale roadways to shore. The integration of all these components, Phoenix caissons, bombardons, whales, and pier heads, into a functioning harbour system required coordination across dozens of government agencies, military commands, and civilian contractors. Vice Admiral John Hughes Hallett directed the Mulberry Harbour development with authority that cut across normal bureaucratic boundaries. His team worked from offices in the Ministry of Transport building in Berkeley Square, London, coordinating with the Admiralty, the War Office, the Ministry of Supply, the Corps of Royal Engineers, civilian engineering firms, construction companies, and transport authorities. Secrecy requirements complicated every aspect of the project. German intelligence could not learn of the artificial harbour plans. That meant construction had to occur at dispersed sites. Workers could not be told the ultimate purpose of the components they built, and transport of finished pieces had to be disguised as routine military logistics. The Deception Plan, Operation Fortitude, actively worked to convince German intelligence that the invasion would target the Pas-de-Calais region rather than Normandy. Part of this deception involved creating dummy construction sites in southeast England, where fake harbour components and invasion craft were positioned to suggest preparations for a Calais assault. Meanwhile, the real Mulberry components were being assembled along the south coast, camouflaged and dispersed to minimise their visibility to German aerial reconnaissance. By early June 1944, the components were ready. 213 Phoenix caissons of various sizes sat in assembly areas from the Thames estuary to Devon. 48 bombardons waited at anchorages in the Solent and other locations. 10 miles of whale roadways, broken into individual pontoons, were staged for rapid deployment. 14 spud pier heads, each the size of a football field, were positioned for towing. Additionally, 59 obsolete merchant ships and naval vessels, called corn cobs, were designated for deliberate sinking to form additional breakwater protection. The scale of what was about to be attempted defied comprehension. The artificial harbours, when fully assembled, would form port facilities larger than Dover, created from components manufactured across Britain, transported across 100 miles of open water through minefields and potential U-boat attack, then assembled on exposed beaches under possible enemy fire, all within 2 weeks of D-Day. The German High Command, monitoring Allied preparations through aerial reconnaissance and intelligence reports, remained convinced that the invasion would target established ports. Their assessment, documented in Oberkommando der Wehrmacht intelligence summaries from May 1944, concluded that Allied forces lacked the capability to sustain a major invasion without capturing a functioning harbour within 72 hours of landing. This assumption shaped German defensive deployments. Heavy fortifications protected the major ports. Defences, while extensive, were designed primarily to delay an invasion force long enough for mobile reserves to counterattack and drive the Allies back into the sea before they could establish supply lines. The concept of artificial harbours never entered German strategic calculations. On June 5, 1944, the invasion armada departed English ports. Among the thousands of vessels crossing the Channel were the tugs towing Mulberry components. The Phoenix caissons, riding low in the water, moved at speeds barely exceeding 4 knots. The bombardons, even more unwieldy, required careful navigation to prevent capsizing in rough seas. The whale pontoons, connected in trains, undulated behind their tugs like massive steel snakes. The crossing took the better part of 2 days for the slowest components. Tug crews navigated through swept channels marked by buoys, maintaining station in convoys that stretched for miles. German E-boats, fast attack craft, attempted to disrupt the invasion fleet but were kept at bay by destroyer escorts and air cover. U-boats, hunted relentlessly by Allied anti-submarine forces, achieved minimal success against the massive concentration of shipping. The Mulberry components, mixed among thousands of landing craft, troop transports, and warships, crossed without significant loss. By June 7th, the first elements were arriving off the Normandy beaches. The assembly process began immediately, even as fighting continued inland. Royal Engineers and American Naval Construction Battalions, Seabees, began the systematic positioning of harbour components according to plans developed over the previous 18 months. The work proceeded with remarkable efficiency despite ongoing German artillery fire. The corncob ships were sunk first, positioned to form an initial breakwater. Crews opened seacocks, flooding the vessels in controlled sequences that sank them upright in designated positions. 59 ships went to the bottom in carefully aligned rows, their superstructures protruding above water to form a barrier against waves and enemy observation. The Phoenix caissons came next. Tug crews maneuvered each massive concrete box into position according to coordinates marked by survey vessels. Once positioned, valves were opened, flooding the internal compartments. The caissons settled slowly, taking hours to sink completely as engineers monitored the process to ensure even flooding and proper positioning. Each caisson had to align precisely with its neighbours to form a continuous breakwater. Survey crews worked constantly, checking positions against plans, making minute adjustments before the caissons became too flooded to move. The work continued around the clock. Floodlights illuminated the assembly sites at night, making the harbour construction visible from shore and drawing occasional German artillery fire. Engineers accepted the risk because the timeline demanded maximum speed. Every day without functioning harbours meant supplies had to be landed directly on beaches, a slower and more vulnerable process. The scale of the operation was staggering. At Mulberry B, the British harbour off Arromanches, engineers positioned 115 Phoenix caissons in an arc extending over 3 miles. The caissons formed multiple breakwaters, an outer line to break the major wave energy, inner lines to provide additional protection and to serve as pier foundations. At Mulberry A, the American harbour off Omaha Beach, 98 Phoenix caissons were positioned in a similar configuration. The assembly required precise coordination, dozens of tugs, hundreds of engineers, thousands of support personnel, all working to transform piles of concrete and steel into functioning harbours, while German artillery tried to disrupt the work and Luftwaffe aircraft made occasional bombing runs. The bombardon breakwaters were positioned in the outer waters, anchored to the seabed with massive chain systems. Each bombardon required careful ballasting to float at the correct depth. Too high, and they would be ineffective at breaking waves. Too low, and they would present navigation hazards to ships entering the harbours. The anchoring systems proved more challenging than engineers had anticipated. The seabed off Normandy consisted of sand and clay that provided less holding power than the gravel and rock bottoms where the bombardons had been tested. Anchor crews had to use heavier anchors and longer chain runs than originally planned. Some bombardons dragged their anchors in strong currents and had to be repositioned multiple times. The whale roadways went in last, once the breakwaters were providing some shelter from waves. Tug crews brought in the pontoon trains and connected them to shore and to the spud pier heads positioned in deeper water. The articulated spans proved their worth immediately, flexing with the tides while maintaining a stable enough platform for trucks to drive across. Engineers made constant adjustments, adding ballast here, adjusting joints there, reinforcing connections that showed stress. The roadways had never been tested at this scale in real conditions. Every day revealed new problems that required immediate solutions. Yet the system worked. By June 14th, 1 week after assembly began, the first Liberty ships were tying up at pierheads in Mulberry Bay. Cargo began flowing across the Whale roadways to shore. Trucks drove directly from the beaches inland with ammunition, fuel, food, and equipment that the invasion force desperately needed. The daily tonnage landed through the artificial harbours climbed steadily. June 15th, 6,000 tons. June 16th, 7,500 tons. June 17th, 8,200 tons. The harbours were approaching their design capacity of 10,000 tons per day, a figure that matched established ports that had taken decades to develop. At Oberkommando der Wehrmacht headquarters in France, German intelligence officers struggled to understand how the Allies were sustaining their invasion without capturing a major port. Reconnaissance reports showed extensive activity off the invasion beaches, but the scale and nature of what the Allies had constructed defied immediate comprehension. On June 18th, German aerial reconnaissance finally obtained clear photographs of the Mulberry harbours. The images, preserved in German military archives, show the massive caisson breakwaters, the floating pierheads, the Whale roadways extending from shore to deep water. The analysts who examined these photographs initially questioned whether they were genuine or some form of elaborate deception. The concept of constructing entire harbours from prefabricated components, transporting them across the channel, and assembling them in less than 2 weeks seemed impossible by every conventional measure. Yet the photographs were real, and the implications were devastating to German strategic planning. Field Marshal Rommel, viewing the intelligence summary on June 19th, understood immediately that the artificial harbours changed everything. His defensive strategy had assumed the Allies would be forced to capture Cherbourg or another port within 2 weeks or face logistics collapse. The Mulberry harbours eliminated that vulnerability. The Allies could now sustain their invasion indefinitely using the artificial facilities, while they methodically captured and cleared established ports. The timeline that German planners had counted on, the narrow window where the invasion could be defeated before establishing secure supply lines, had evaporated. Rommel's chief of staff, General Hans Speidel, wrote in his post-war memoir, "The artificial harbours represented a revolution in amphibious warfare that we had not anticipated. Our entire defensive concept rested on the assumption that the Allies required capture of established ports. When we realized they had constructed their own harbours and were landing thousands of tons daily through these improvised facilities, we understood that the strategic situation had fundamentally changed. The invasion could not be defeated through defence of ports because the Allies had made ports irrelevant to their initial operations." The catastrophe that nearly destroyed the Mulberry concept arrived on June 19th. A severe storm, the worst to hit the English Channel in June in over 40 years, descended on Normandy with winds exceeding force 6 on the Beaufort scale. Waves over 6 feet high battered the artificial harbours. The storm continued for 3 days, reaching peak intensity on June 21st. At Mulberry A off Omaha Beach, the Bombardon breakwaters failed first. The anchoring systems, already stressed by currents stronger than anticipated, could not hold against the storm forces. Bombardons broke loose, crashed into each other, and either sank or drifted uselessly. Without the outer breakwater, waves pounded directly against the Phoenix caissons. Several caissons, already weakened by the constant battering of the previous 2 weeks, cracked and began to flood unevenly. Some tilted, some broke apart. The failure of the outer defences exposed the pier systems to the full force of the storm. Whale pontoons, designed to handle normal wave action, could not withstand the extreme conditions. Joints failed, pontoons broke loose, articulated spans twisted and bent. The spud pier heads, their legs driven into the sandy seabed, held their positions, but the roadways connecting them to shore disintegrated. Ships tied to the pier heads rode out the storm, but cargo operations ceased entirely. At Mulberry Bee off Arromanches, the British harbour weathered the storm better, but still sustained significant damage. Some bombardments broke loose, several Phoenix caissons cracked, portions of the Whale roadways failed. The difference was that enough of Mulberry Bee survived to be repaired and returned to service. Mulberry A, the American harbour, was essentially destroyed. American engineers surveyed the damage on June 23 when the storm finally abated. The assessment was grim. Approximately 80% of Mulberry A's components were destroyed or too damaged for repair. The harbour could not be rebuilt in time to be useful. General Eisenhower faced a critical decision. The storm had destroyed one of the two artificial harbours that his supply plan depended upon. Cherbourg had not yet been captured. The invasion force was growing daily as reinforcements poured ashore, but without adequate port facilities, the entire operation risked becoming logistics-bound. Eisenhower decided to strip useful components from the ruins of Mulberry A and use them to repair and enhance Mulberry B. American engineers salvaged Phoenix caissons, Whale pontoons, pier heads, anything that could be towed to the British harbour and integrated into its systems. The British harbour would have to serve both the British and American sectors until Cherbourg could be captured and made operational. The repair and enhancement of Mulberry B proceeded through late June and early July. Engineers replaced damaged caissons, repaired pier systems, strengthened breakwaters. By July 1st, the harbour was handling 9,000 tons per day, actually exceeding its original design capacity. The destruction of Mulberry A and the damage to Mulberry B demonstrated both the vulnerability and the resilience of the artificial harbour concept. The structures were not invulnerable. Extreme weather could destroy them, but they could also be repaired, modified, and operated under conditions that would close conventional harbours. More importantly, Mulberry B continued functioning long enough for Cherbourg to be captured and cleared. American forces captured Cherbourg on June 26 after fierce fighting. German demolitions had destroyed the port facilities with typical thoroughness. Every crane was toppled, every warehouse demolished, every dock destroyed, every lock gate blown, and the harbour waters filled with deliberately sunken ships and obstacles. Allied engineers estimated it would require weeks to restore even basic functionality. The first Liberty ships entered Cherbourg harbour on July 16, 3 weeks after capture, and even then could only unload at improvised facilities. The harbour did not reach its pre-war cargo handling capacity until late August. Without Mulberry B operating throughout this period, the Allied logistics system would have collapsed. The artificial harbour sustained the invasion during the critical weeks when Cherbourg was being cleared and when other ports remained in German hands. From July 1st through November 1st, when Mulberry B was finally superseded by the reopened ports, the artificial harbour handled over 2.5 million tons of cargo. That tonnage included ammunition for the artillery that supported the breakout from Normandy, fuel for the tanks that raced across France, food for the armies that liberated Paris, and medical supplies for the field hospitals that saved thousands of lives. The daily rhythm of Mulberry B's operations demonstrated what could be achieved through systematic engineering. Liberty ships arrived in convoy, typically 6 to 8 vessels at a time. Each ship tied up at one of the spud pier heads and began unloading immediately. Cargo nets and crane systems transferred ammunition, rations, fuel, and equipment onto trucks waiting on the Whale roadways. The trucks drove directly from pier heads to shore, a distance of over a mile, then continued inland to distribution points. The cycle repeated continuously, 24 hours a day, 7 days a week, in all weather conditions short of severe storms. The harbour handled vehicles as well as cargo. Sherman tanks drove off LSTs directly onto Whale roadways and across to shore. Trucks, jeeps, artillery pieces, all manner of wheeled equipment made the journey across the floating roadways. The Whales proved remarkably durable, despite the constant traffic and harsh marine environment. Maintenance crews worked continuously, replacing damaged pontoons, repairing joints, adjusting ballast systems, but the basic design held up far better than many engineers had predicted. The strategic impact of Mulberry B extended beyond the tonnage statistics. The harbour fundamentally changed German defensive calculations in ways that rippled through their entire command structure. Oberkommando der Wehrmacht planners had structured their defence of France around the assumption that Allied supply limitations would force a battle for ports early in the campaign. German mobile reserves were positioned to counterattack and recapture any port the Allies seized, on the assumption that destroying Allied supply facilities would cripple the invasion. The existence of Mulberry B made this strategy irrelevant. Allied supplies continued flowing regardless of whether Germans recaptured ports, because the primary supply line ran through facilities the Germans could not threaten with ground forces and could barely reach with artillery. The psychological impact on German commanders was profound. General Günther Blumentritt, Chief of Staff to Field Marshal Günther von Kluge, Commander-in-Chief West from July 19th, wrote in his post-war interrogation, preserved at the United States Army Military History Institute, when we learned that the Allies had constructed artificial harbours and were landing supplies at rates exceeding many established ports, we realized the fundamental basis of our defensive planning was flawed. We had assumed logistics would be the Allied weakness, that their dependence on ports would give us opportunities for counterattack and disruption. The artificial harbours demonstrated that Allied industrial and engineering capacity exceeded our estimates by orders of magnitude. If they could build harbours from scratch and make them function under combat conditions, what other surprises awaited us? The workers who had built the Mulberry components in England followed the harbour's operations with intense interest. For most, the nature of what they had been constructing only became clear after D-Day, when censorship restrictions eased and photographs appeared in newspapers. The massive concrete boxes they had poured, the steel structures they had welded, the pontoons they had assembled, all of it had come together into functioning harbours, sustaining the liberation of Europe. Mary Anderson, a welder at one of the Phoenix construction sites in Southampton, recalled in a 1984 interview conducted for the Imperial War Museum, "I had spent 6 months welding, reinforcing bars into wooden forms that were then filled with concrete. The work was hard, the hours long, and we had no idea what we were building. When I finally saw photographs of the Mulberry harbours in Normandy and realized those massive concrete structures were what we had made, I felt such pride. We had built something that helped win the war. Every weld I made, every connection I completed, it all mattered. That knowledge sustained me through many difficult days." The engineering teams that had designed the Mulberry systems watched the harbour operations with mixed feelings of pride and concern. Every problem that arose offshore revealed shortcomings in the design or construction that had seemed adequate in planning but proved marginal in practice. Yet the system worked. Lieutenant Commander Alan Beckett, whose whale roadways carried the bulk of cargo from pier heads to shore, visited Arromanches in September 1944. His report, filed with the War Office Engineering Section, balanced technical criticism with recognition of achievement. "The whale pontoon roadways have performed beyond my most optimistic predictions. We designed them to last 3 months under moderate traffic. They have now operated for over 4 months under heavy continuous use. Approximately 30% of pontoons have required replacement due to structural failure or storm damage. The articulated joints show wear exceeding design parameters, but continue functioning. The most significant surprise has been the system's adaptability. Engineers at the site have modified, repaired, and improvised solutions to problems we never anticipated during development. This field adaptation has been as important to success as the original design. The liberation of France and Belgium through autumn 1944 opened additional ports that gradually reduced dependence on Mulberry. B. Antwerp, captured in early September but not operational until late November after the Scheldt estuary was cleared, eventually became the primary Allied supply port. Marseille and other southern French ports, captured during Operation Dragoon in August, handled increasing tonnages. By November, when storms finally forced closure of Mulberry B, the Allied logistics system no longer depended on the artificial harbour. Its mission was complete. The final statistics of Mulberry B's operations reveal the scale of achievement. The harbour operated for 159 days, from June 14 to November 19, 1944. During that period, it handled 2.5 million tons of cargo, equivalent to approximately 15,000 tons per day, averaged over the full operational period. This exceeded the harbour's design capacity and matched the throughput of many established ports. The harbour serviced over 11,000 vessels, ranging from small coastal craft to large liberty ships and tankers. Over 500,000 vehicles crossed the Whale roadways, including tanks, trucks, artillery pieces, and support equipment. The cost of the Mulberry programme, both harbours combined, was approximately £42 million sterling, equivalent to roughly £2 billion in early 21st century values. This represented a massive expenditure, but trivial compared to the cost of the invasion as a whole. More importantly, the artificial harbours were not an additional expense, but rather an alternative to the casualties and delays that would have resulted from assaults on fortified ports. Measured against the lives saved and the strategic flexibility gained, the Mulberry programme represented exceptional value. The German perspective on the artificial harbours evolved from dismissive disbelief to grudging respect as the war progressed. In November 1944, German military intelligence published an assessment of Allied logistics capabilities that included extensive analysis of the Mulberry harbours. The report, discovered in German archives after the war, concluded, "The artificial harbour installations at Arromanches represent a technical achievement of the first order. The Allies demonstrated engineering and industrial capabilities that exceeded our estimates by a substantial margin. The concept of constructing complete harbour facilities from prefabricated components and assembling them under combat conditions was not considered within our defensive planning. This oversight contributed significantly to our failure to defeat the invasion during its vulnerable early stages." Post-war analysis by military historians and engineers consistently identified the Mulberry harbours as critical enablers of Allied victory in Normandy. The consensus view held that without artificial harbour capacity during June through August 1944, the invasion would have faced severe logistics constraints that might have prevented the breakout from the beachhead. Cherbourg's capture and clearing took longer than Allied planners expected. Other ports remained in German hands until September. Mulberry B filled the gap between the invasion and the restoration of established port capacity. The technology and concepts developed for the Mulberry project influenced post-war port engineering and amphibious warfare doctrine. The idea of portable harbour facilities reappeared in various forms in subsequent decades. The United States military developed expeditionary pier systems for rapid deployment. Commercial shipping embraced containerization, which emphasized standardized cargo handling that could be adapted to improvised port facilities. The flexibility and adaptability that characterized the Mulberry design became principles in contingency planning for future amphibious operations. In 1984, 40 years after D-Day, a reunion of Mulberry veterans was held at Arromanches. Engineers, construction workers, tug crews, and military personnel who had participated in the harbour programme gathered at the small Normandy town that Mulberry B had made famous. The remnants of Phoenix caissons still dotted the water offshore, concrete monuments to engineering achievement. The reunion participants, many now elderly, shared memories of the frantic pace of construction, the terror of towing massive structures across mined waters, the satisfaction of watching the harbour operate despite German artillery fire. Major General Robert Ross, who had commanded engineering units during the harbour assembly, addressed the reunion attendees. His words, recorded in the local newspaper and later in the Imperial War Museum archives, captured the significance of what they had achieved. "We came to France 40 years ago as engineers, sailors, and soldiers, tasked with building something that naval experts claimed was impossible. We were told to construct harbours where none existed, to create shelter from storms using floating concrete and steel, to assemble port facilities in days that normally required years to build. We succeeded beyond the expectations of our commanders, and certainly beyond what our enemies believed possible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.